Awesome. Well, good morning, everybody, or afternoon to those who are on the East Coast. On behalf of the Candrone team, I'd like to thank you for taking your time to attend the webinar today, despite some technical difficulties that we had at the beginning here. So the LiDAR processing topic has been a topic of interest that we've seen throughout the social media channels. And today we're super excited to address it. We can expect the presentation to go for about 40 minutes. And just a couple of housekeeping items. The webinar will be recorded on our YouTube channel. So it will be posted on our YouTube channel, and our various social media channels. So be sure to subscribe to our channel and follow us if you want to rewatch the webinar. We'll be taking your questions throughout the webinar. So please input the questions into the question box as we go through here, and we'll be happy to address it at the end. And we'll be just shutting down our cameras to avoid any distractions before, as we go throughout the presentation here. So without any further ado, just a quick introduction. My name is Van. I'm the Digital Marketing Manager here at Candrone, and I'll be your host for today.
And my name is Camille, and I'm going to be the one teaching you all about LiDAR 360 today.
All right, I'm danl, Solutions Advisor, helping you choose the right product for your desired outcome.
My name is Codymccoll, and I'm with GreenValley International, and I'm a Customer Success Manager.
Thanks, Cody. Okay, so on the agenda today, we'll start off by having a quick overview of what LiDAR 360 is, the different modules that you can get with the software, and just a quick history about GreenValley International. And then once we've completed that, we'll jump into kind of the meat and bread of the presentation, where Camille will go through the LiDAR data processing workflow, and we'll end it with a question and answer session at the end of the presentation here. So I know you guys have already voted, so we can skip this slide. Yeah, we'll continue on here. So yeah, I'll pass it back to Cody. Hopefully you guys can hear him now with an introduction to GreenValley.
Hello again. GreenValley International is a turnkey solutions company that offers 3D mapping technologies and products for a wide array of industries. The company's founder, Dr. Guo, received his PhD from UC Berkeley before becoming an adjunct professor at UC Merced. In 2012, he founded GreenValley International, headquartered out of Berkeley, California, with a main target of changing the software side of LiDAR post-processing, specifically that utilized by the forest management industry. This led to the development of the LiForest software, which in turn led to the creation of LiDAR 360. LiDAR 360 is a versatile LiDAR point cloud post-processing software. After great success within the software realm, the company then broke into the hardware side of the industry, which led to the production of a number of devices from UAV and fixed-wing aircraft for airborne laser scanning to our famed LiBackpack and LiPod and LiMobile for terrestrial laser scanning. And the company now has partners in over 30 countries in the world and is continuing to grow with each new day. As mentioned earlier, I'm the Customer Success Manager for GreenValley International's North American market and the branch manager at our Berkeley, California location. I graduated from UC Berkeley with a degree in geography and a minor in geospatial information sciences and technologies. I have a personal passion for UAVs and everything about the ever-evolving world of LiDAR.
Thank you, Cody, and I'll pass it back to Dan here.
All right, thanks, Van. Thanks, Cody. So in this webinar, we'll be focusing on the basics of LiDAR 360, which is the software used to process and manage LiDAR files, offering a comprehensive data analysis solution. Now, there's no requirement for internet connection, and they can process terabytes of data locally, which means you can take it out on a laptop and use it in the field. LiDAR 360 can be licensed with add-ons, and they reside right inside the menu bar, giving you access to additional functionality for analyzing your point clouds. We'll go over some of those in the upcoming slides. The recommended specs are a Windows computer with at least 8 GB of RAM and a dedicated graphics card. So if you're running a Mac, you may consider using Boot Camp or some kind of virtual emulation type software. Licenses are perpetual, meaning you pay for one time for one seat, and that comes with a floating license manager allowing you to install and manage those activations on other computers. The pricing for LiDAR 360 at this time of the webinar is $3,000 US. Now, The terrain module allows you to create digital terrain modules and contour lines from any point data. The output is essentially a bare earth model, which allows you to scrub for any objects such as trees from your point cloud. This is really important for a variety of use cases, such as analyzing the topography and doing slope calculations. Pricing for the terrain module is $1,500 US. Now, the forestry module allows you to collect forest inventory data from your point clouds, such as the tree location, i.e. the latitude, longitude, the diameter and breast height, which is a very useful measure in forestry. Crown metrics and trunk straightness are just some of the data you can actually capture within it. Having this data allows you to understand your plots better. The forestry module is $1,500 US. And the last module inside LiDAR 360 is the power line module, providing you with an automatic and manual classification of power lines, transmission towers, vegetation, and other objects of interest. It can be used to detect danger points, such as vegetation encroachment and tree fall hazards onto those power lines. You can quickly generate reports that can be exported into KMLs. The power line module can be purchased as an add-on for $1,000 US. It can also be purchased as a standalone tool for $6,000 US on its own. Now, GVI also does have some more industry-specific modules coming out, such as geology and the mining modules for it. They can do volumetric calculations, but we'll just focus on these modules currently on the market.
Thank you, Dan. So what you might be wondering what data is compatible with LiDAR 360. So essentially any LAS, LAZ, E57 or ASCII data is compatible with the software. And obviously the full GVI LiDAR solution like the V70 or the 220N is compatible. The L1 data is also compatible. As you'll see in the coming slides, we'll use that the L1 data as an example. And of course, the hover map data is also compatible with LiDAR 360. So to get into the core of the presentation, now this is the processing workflow that we use here internally at Candrone. So that's broken down into 5 steps, starting off with the strip alignment, then we get into removing the outliers, we go into the ground classification and accuracy assessment, and then finally generating a service model. So without any further ado, I'd like to pass it on to Camille to talk about the workflow.
Thanks, Van. All right, so to get into it, the first thing we want to start with is strip alignment. So UAV LiDAR data is acquired in these sort of overlapping flight lines, which I like to refer to as strips. And a Boresight calibration is the process of correcting misalignment between the adjacent LiDAR strips in your raw point cloud data. So the calibration just really helps to remove systematic errors and minimize any random errors in your data. So some of the sources of measurement errors are from either GPS, IMU, or any laser sensor errors. Additional factors creating errors include flight altitude, piloting skills, wind, other environmental factors that can impact the flight's trajectory, causing misalignment in your data. So is strip alignment always required? The answer is no, not always, but generally speaking, it is a good practice to include strip alignment in your point cloud processing workflow. Strip alignment does not replace calibration of a system that hasn't been serviced by GVI annually. And note that this process that we're about to go over for strip alignment is also doable in LiDAR reference for those customers who have a LiDAR V or a LiDAR V70. You can do this Boresight correction in LiDAR reference. So how do we examine for shifts? Basically, there's going to be kind of 3 things that we're going to go over shortly. First, we're going to use the profile tool to look at cross sections of our data, just like the image on the right. And then we want to look at flat roof surfaces. And lastly, we're going to view the point cloud by time. And we'll go over these tips shortly. So what if I have a DJI L1 L1 point cloud processing in DJI Terra has a built-in strip alignment process, so you don't actually need to run a strip alignment on your DJI L1 data. Further, the output folder from the L1 doesn't contain a readable SPEC file right off the bat, and furthermore, converting that trajectory information into the SPEC file and then importing it appropriately would be a bit more of a integration process. So just know that if you have an L1, it's doing the strip alignment for you in DJI Terra, so you'll just have an LAS file output that's already strip aligned. So first things first, we want to import the data. So load in your point cloud by selecting the LAS file, or if you have a LiDAR file, if you created your point cloud either in LiAcquire or LiGeoReference. And now to do this Boresight correction that I've been mentioning, we need two things. So first, of course, we need the point cloud, which we have hopefully just imported. And then secondly, we need a POS file, which contains all of the trajectory information from the drone flight. So we want to import this trajectory. So use the Open Trajectory File button to load in this POS file from your flight. So the XYZ, pitch, roll, and yaw data points will then pop up, as you can see on this slide, and then you can just hit Apply All on this window, and they should the trajectory should pop up. So now that you have our trajectory data loaded in, what we want to do is actually just remove any poor quality data. So the worst data is all at the turns, basically. So we want to make sure that we remove that. So as the LiDAR's IMU has to reorient itself during this turning motion, it can cause worsening measurement accuracy. So it's best to just trim out that data. So what we want to do is click on the Select on Trajectory button, and then select the parallel flight lines one by one, beginning to end, cutting out the turns and any erroneous start to finish flight paths. And just to note, there is another way to do this. You can use that draw polygon tool to select the parallel lines, cropping out the edges or turns from the polygon, and then the software will do the flight path clipping, splitting for you automatically. But I just prefer the first method, just you have a bit more precision in selecting the start and end of each flight path. So then you want to click Split Trajectory, and then once that process is done running, you'll have to add the result to the project. So the result will be a separate point cloud for each flight line. So you can remove the original point cloud by right-clicking on the point cloud in the Layers menu and hitting Remove. That just helps keep only the files that we're working with in the Layers menu, so you don't get confused with older files. They're saved, they're just not in your viewer. Then back under the Boresight ribbon, you want to click on Match Point Cloud and Trajectory. This will just match the trajectory lines, the colors basically, with the same color on the point cloud. All right, so now while we look at doing the Boresight calibration, it's also super helpful, like I mentioned a bit earlier, to look at a thin slice of the data using the profile tool so that you can actually just visualize the kind of the before and after of the Boresight calibration. So you want to click on the profile tool and take a 10 centimeter cross section. So you just want to type into that buffer tool box the size of your cross section, so 0.1. And then that's the slice of your data. And then after that, you can click Boresight calibration in the Boresight ribbon. And then once you've got that up, you can click calculate in the calibration window. And once it's done calculating, you should take note of the RMSE, the root mean squared error values before and after. So typically what you'll see is that the Boresight calibration can tighten up the data from 2 to 4 centimeters. So very importantly, press apply. So after you press calculate using the default settings, you need to press apply to actually have the calculation applied to the point clouds, or else you won't actually be adjusting anything. So for this point cloud, the Boresight correction was able to tighten up the point cloud by 1.5 centimeters from an RMSE of 7.5 down to an RMSE of 6 centimeters. So then you can close out of this tool, and you can also exit out of that profile window. And lastly, there's just one more tool for this Boresight ribbon. So lastly, the tool is called cut overlap. This doesn't actually delete any data, but rather just classifies the points as overlap in areas where you have overlapping swaths. So essentially, the overlap class includes all the points in the outer angles of the LiDAR sensor's field of view. So which it just leaves you with the best data in the unclassified class, which is what you should use for the ground classification. So now that the Boresight correction has been applied to our strips of point clouds, we want to merge the point clouds back into one file so that we don't have 5 to 10 different point clouds. So in the toolbox under data management, click on point cloud tools and then select merge and have that tool run. So once that tool has run, you'll have your merge point cloud, and you can remove the other point clouds from earlier. Now we want to remove outliers. It's always a really good idea to run an outlier removal algorithm on your point cloud to get rid of any noise above or below your point cloud. But why do we even have this sort of noise in the first place? So the main contributors to noise include systematic errors, atmospheric, so particles in the air, usually fog, as well as environmental factors, including reflection, scatter, precipitation, and bodies of water. And lastly, birds often create a fair amount of noise. So there are 2 parameters under this tool. So we've got the neighbor points, where the default value is 10. And this parameter specifies the number of points required in the neighborhood to calculate the average distance to each point. And then the multiples of standard deviation parameter is the factor that's multiplied by the standard deviation to calculate the maximum distance allowance. And the default value here is 5. So without bogging you down too much, basically, if you have a few outliers, use the defaults. And if you have a larger number of outliers that are kind of clouding your data set, what you can do is increase the number of points, the neighbor points, to 15 to 20. And you can decrease the multiples of standard deviation factor to 3 or 4. And these settings will just help run a heavier filter to remove more outliers. All right, so now it's time to classify ground points. There are 2 measurements that you should make first before you want to do the classification. So if you do these 2 measurements, you'll be able to more successfully set up your ground class algorithm to work with your specific point cloud. So firstly, if you have buildings in your scan, you want to measure the longest building length using the top-down view of the point cloud and the measure tool. And then as you can see in this GIF right now, that the profile tool is another tool you can use to measure the greatest terrain angle in your scan. So you want to take multiple cross sections throughout your point cloud to find the steepest terrain. And then once you're still in that profile tool, you can use the angle tool measure tool to roughly measure that terrain angle. So you want to take note of that, the longest building length. In this case, it was about 26 meters. And then you also want to take into consideration or remember that max terrain angle. All right, so once you've done those measurements, you can open the ground classification tool and input those max building length and the max terrain angle. If your scan area has no buildings and is relatively flat, just feel free to use the default settings. And lastly, change the reduce iteration angle when edge length is less than 1 to 0.5. And this just helps increase the point density of your ground class, which can't go wrong there. And then you can run this process. And once it's finished running, doing the classification, you can actually just check your density of your ground points by using the density measure tool under the tools ribbon. So here I have a point cloud from the DJI L1. And in this little video, I'm toggling on a couple different ways to visualize your point cloud, including by RGB colorization and by elevation. So after running the ground class tool and you find that your project application maybe requires a bit more of a denser ground class, you can actually just use the tool called classify medium ground points to increase that ground class point density. But keep in mind, if you do choose to use this tool, you will be selecting points for your ground class from a greater variance in measurements. So you'll be sacrificing a small amount of accuracy by using this median ground points tool. All right, so we will now use this L1 dataset to go over how exactly to do an accuracy assessment in LiDAR 360. So if you haven't already classified ground points, this would be the next step before assessing accuracy. I doubt you're doing this in real time, but yeah, just know that you want to have ground points classified so that we can do the accuracy assessment only on the ground points and not the whole point cloud. So in the toolbox under strip alignment, select control point report. And here you can import your ground control points in a text file format with the GCP XYZ location information. So just note, if you have a GCP ID number or something, that column can also be imported into the text file format, but you'll just make sure that you need to hit ignore on that column so that the program doesn't mistake that column for an XYZ position. All right, so once you've loaded in your GCP text file, you want to uncheck half of the points to use as final checkpoints at the end. So uncheck half and just leave them, forget about them for a minute. And then with the half that is selected, you want to click calculate. And then once the calculation has run, you want to click export. And you can save this export file of the statistics of half of the points, basically showing the DZ values from where the point cloud is sitting compared to your GCPs. All right, so you can also use this profile, the same profile tool as we used before, to inspect these GCPs in relation to the point cloud, just to get a better visualization of where the point cloud is sitting in relation to these GCPs. But keep in mind that this is mainly a vertical check, right? We're looking at the DZ values, unless you have a colorized point cloud, which is usually a good way of doing things, or you have set out some checkered targets or spherical targets to see or check the horizontal accuracy. So you're just looking at the DZ values here. Sorry, okay, so after the elevation adjustment process is done, oops, my bad, I skipped a slide. So basically after you've exported that file, if you want to have your point cloud fit more tightly to your GCPs, you can use the tool called elevation adjustment under projections and transformations. So select elevation adjustment and then input that file that you had just saved out of the control point report tool, the one that we press export and saved out, and then you input it here for the elevation adjustment, and then you can hit OK to run the process. So after the elevation adjustment process is done, add that new point cloud to the project. And then you can open up that control point report tool once more. And then again, you want to load in your GCPs here. And this time, you want to select the points that were not selected in the original assessment. So all of the ones that we had unchecked at the beginning, those are the ones that we want to have checked here and not the ones used for the elevation adjustment. So once the assessment points are selected, you can hit calculate to produce this final accuracy report statistics. And here you'll see that the RMSE units are in meters. And for this example, this L1 point cloud has an accuracy of under 5 centimeters. But note just that the GCPs used for this accuracy assessment were all on hard surfaces. So just keep in mind that the accuracy could be a bit lower in soft surface areas, like vegetated areas.
All right, thank you, Camille. I know that was a long stint, so we'll just give you a quick break here. So quick pop quiz, is strip alignment always required? So I want you to vote in this poll that's coming up here. Okay, thank you for voting. And for those of you that voted true to strip alignment is always required, I believe that answer is false. You don't have to always do the strip alignment. Okay, so we'll close that. Okay, and I'll pass it back to Camille to talk about generating some surface models.
Thanks, Van. So yes, so the sort of last section here is how do we generate a DEM, DSM, and contours. So first of all, what even is a digital elevation model and how do we make one? So after classifying ground points, the DEM is created by interpolation methods to fit a continuous surface. So each interpolation method, there's 3 options in the DEM tool, you'll see. Each of these interpolation methods has a slightly different underlying model, but the basic premise is that you're going to be using the points that are classified as ground, and the DEM model will fit a surface through these ground points to provide a continuous model of the ground. So if you had a thick forest that had areas where you had no pulses that were able to penetrate to the surface, you would have some holes in your point cloud that can really degrade the level of detail that you can get in your point cloud and in your DEM. So if you have only 1 point every meter or 2, it's going to be very, very difficult to make a 1 meter by 1 meter DEM. So generally you would need at least 3 points per meter squared to make a 1 meter by 1 meter DEM. So how to check for the point density? Well, you want to kind of just do this little point density check using that point density tool under the tools toolbar to just double check that you have the necessary point density in your ground class before you go ahead to use that DEM tool. So I'm just going to quickly show you how easy it is to make a DEM and a DSM and some contours. So under the terrain module, what you want to do is select DEM and choose your raster cell size. For this example here that you guys are seeing, we're making a 1 meter by 1 meter DEM. Then you want to choose your interpolation method. For this example that you see, we chose tin, which is a very common method, and then you can hit run. So once your DEM raster is outputted, What you can do to better visualize your DEM in 3 dimensions is to use the Convert Raster to Lie Model tool. Then once you have that lie model loaded into the project, you can right-click on the DEM raster in that layers menu and remove it from the project. It's still saved in your project folder, but it just needs to be removed from the view in LiDAR 360 since it's a 2D object. It's a raster image that's 2D. So once you remove that image, on the left-hand side of the visualization toolbar, make sure you toggle that viewer back into 3D. And then the DSM, the digital surface model, which is produced from the last return LiDAR signal, which includes heights of objects such as vehicles, buildings, and vegetation, as well as the terrain surface. To make this DSM, we want to go under that terrain module, same as the DEM, and choose DSM instead. And then you want to also choose your raster cell size and your interpolation method, and then you can hit run, same as the DEM steps. So same thing, to better visualize the DSM output, convert the DSM raster into a lie model to view in 3 dimensions. Of course, it's not mandatory, but just helps visualize since it is a 2D output. All right, so now we're going to generate contours. So to generate contour lines, the tool is under terrain module as well, and it's called Point Cloud to Contour. Here you can set the minor, basic, and major spacing, and then choose either a shapefile output or a DXF file output. The shapefile, of course, is a GIS software file type, and then DXF is it's compatible with AutoCAD. To view the contour output in LiDAR 360 quickly, you can just choose the shapefile option and click OK. So once the point cloud to contour process has run and is finished processing, you can add that shapefile contour output to the project to visualize. You can see some very detailed contour lines here. And yeah, you can just toggle off any of the other layers to better view the contours on their own. And one last tool that you should note is the TIN tool, which allows you to generate a TIN model, which is a great tool for viewing and editing the classification results if you were to have any outliers in your ground class. So either you could use a lie model to view this and see any outliers, or you could use this TIN model. So the TIN file is also easily imported into other softwares, other GIS softwares like ArcGIS. So yeah, that's kind of a nifty one because the lie model tool is only compatible with LiDAR 360. So that gives you a bit more flexibility. So yeah, that's all from me for now. So thanks for listening, and I'll pass it back over to Van.
All right, thanks, Camille. So the next section here, we'd like to just kind of get an idea of who's looking to get a trial key for LiDAR 360. So I'll just put up a poll here. When you vote, we'll be able to segment your email into a list that we can send out the key to. So please vote accordingly if you'd like a trial key here. Okay, we have about 65% people that have voted. I'll give it another 30 seconds and then we'll continue on from here. Okay, we'll close the poll now. Awesome. All right. Yeah, thank you guys for being patient with us. Unfortunately, with that technical difficulty at the beginning there. So right now we'll open up to question and answer period. So I'll just look through kind of the question box here that we have, and I'll read it out, and then yeah, you guys can go from there. So the first question we have from Eddie, he's asking, so LiDAR takes a lot less processing power than photogrammetry. Would you agree with that?
Yes, I can answer this one. Yes, that is very true. The processing for photogrammetry is way, yeah, I don't know exactly the ratio, but yeah, the LiDAR processing is way faster. It's just mainly because the LiDAR data is, each point that you're looking at is already this three-dimensional point, this XYZ point. From photogrammetry, if you want to make a 3D model, you have to make these 2D images into a 3D model, which taking an XY and having enough processing power to make it into an XYZ is infinitely more processing intensive. So yeah, you're right on with that, that it's going to take a lot more processing to do photogrammetry 3D models.
Okay, thank you, Camille. The next question from Eddie again. So does DJI Terra does the Boresight correction, does it do a good job on its own?
Does it do a good job doing the strip alignment? Is that what you mean?
Yeah, I think that's the question is if Terra does a good job of doing the strip alignment for one data.
Yeah, it does do a pretty good job. There still sometimes is a bit more noise since there's just like a high point density. So it's still recommended by DJI to run a outlier removal algorithm on it. So once you have your LES file from DJI Terra, you can bring it into LiDAR 360 and do the outlier removal tool to just kind of minimize any of that fluff. But unfortunately, just from my own perspective and experience, like there are no output statistics from DJI Terra, so there isn't a perfect way of kind of seeing that change that happened during the Boresight correction. So because DJI Terra is meant to be like very user friendly and one click, there's only like a couple options, it's meant to just be very user friendly in that sense. And it is the kind of double-edged sword there is that it's a little bit less
involved,
able to, yeah, you don't have as much capability to dig into it the same way that you can with using LiDAR reference with the GVI software product.
Great, thank you, Camille, again. The next question is from Clarence. So he's asking, does this classification process work with photogrammetry-based LAS / LAZ as well? And then he saw that it did not require returns captured by the sensor.
Yes, you can use an output from a photogrammetry model LAS and do this classification. That's no problem. And then, sorry, what was that second part to that?
It says he saw that it did not require returns captured by the sensor. So.
Oh, yeah. So it doesn't have to have a attribute that is referring to the return number. In that sense, for your photogrammetry LAS point cloud, it will just probably all say first return or something, or it won't have that attribute, but it won't matter.
Awesome. So the next question comes from Aubin. He's asking, or they're asking, is there a way in LiDAR 360 to import an area of interest that all of the products could be clipped to?
Yes, there is, that you can import a shapefile of your project area, and then yeah, you can. There's like a cropping tool.
Okay. So Emily asks, I noticed you all did not do trajectory adjustments alongside Boresight. Why is that?
Yeah, so the trajectory adjustment, I believe it's actually not really available in LiDAR 360. It's available in LiDAR reference if you have a V70 or LiDAR V. Cody, correct me if I'm wrong on that, but I'm pretty sure it's just in LiDAR reference. and that trajectory adjustment is sort of, it's recommended only if you have data that needs extra cleaning up. It's just best practice not to manipulate your data as much as possible. So if you don't need it and your data is looking good and you had good data acquisition practices and you're seeing data that's falling with, you know, that accuracy or that Boresight correction within the system accuracy, we would suggest that you don't really even need to use that elevation, or sorry, the trajectory adjustment tool. That's only if you had some interesting conditions and are seeing data that's lower quality. But yeah, it's definitely not mandatory.
To piggyback off of what Camille said, you can do it in LiDAR 360, but as she stated, in most cases it's not necessary. But if it is something that you want to do just as a secondary method, then you can do it within LiDAR 360 and also LiGeo reference.
Okay, thanks, Cody.
Thanks, guys. So the next question is from Aubin again. He's asking, is there a main reason to use LiGeo reference and then LiDAR 360? It appears as though 360 performs all the same processes / functions.
Yeah, so LiGeo reference is specifically for GreenValley International customers who have a LiDAR B or LiDAR B70 or one of their LiDAR systems, and need to do that point cloud creation process where the main reason you need LiGeo reference would be to make that point cloud where you combine the IMU, the GPS, and the laser data, the raw laser data, into that point cloud. So from there, once you've created that point cloud, you can for sure 100% take that point cloud LAS or LiData file and bring it into LiDAR 360 and do the rest of your processing there. Or the way that they're developed, I guess Cody can talk to this a bit, but the way that they've developed LiGeo reference is they've added a lot more features. Like, I think that was kind of the base premise for LiGeo reference, but since over the last kind of couple years, they've added a lot of features, including doing all that strip alignment and removing outliers. There's a lot of more functionality in LiGeo reference that you can still that you can do. So there's a bit of overlap between some of the features in both of the softwares, but you need LiGeo reference if you're going to create that point cloud, if you own a GVI LiDAR system, and then everything else can technically be done in LiDAR 360. Cody, do you want to add anything to that?
Yeah, so I mean, you were right on the button. LiGeo reference is technically considered a pre-processing software proprietary to GreenValley products, where LiDAR 360 again is a post-processing. It gives you more functions for analysis, and it can be you can utilize data collected by other devices. With LiGeo reference, it does allow you to do everything that DJI Terra does automatically. This gives you the ability to do it manually, to do a couple extra features. You can colorize your point cloud if you get a device from GVI that has a camera built into it. But again, yeah, so they are very similar. It's just that LiGeo reference was designed with the aspect of, if you get a GreenValley product and you don't have a LiDAR 360, for instance, you use a different post-processing software, you can still produce a file that will give you the ability to input it into a different post-processing software.
Awesome, thank you, Cody. So just to address one of the audience concern with that you couldn't see some of these videos on the screen clearly, we'll be sure to send out the kind of the presentation deck at the end of this webinar so that you can review it also, and hopefully that clears that up for you. So the next question is from Domingo. He's asking if there is a Spanish version of the application, which I assume is LiDAR 360.
Cody, I think you might be on mute.
So I do believe that it is possible to have it translated into a Spanish reading, because again, we do have clients all across the globe. So I would have to double check on that right now. But yes, I do believe that it is possible to have a Spanish version.
Thanks, Cody. The next question is from Jesse. He's asking if can the tree location / trunk measure routine be used with airborne LiDAR data?
I can give that one a go. So typically no. So the kind of features that Dan was talking about, he was sort of encompassing both of the modules within the forestry module. So there's an ALS, an airborne LiDAR scanning module for forestry, and there's a terrestrial. So if you have you're on the ground scanning, you want to use that module, you would be able to get those tree trunk measurements, those DBH values a lot more clearly. But no, it's kind of not quite there, in the sense that if you can kind of make some estimates. You could do a regression model analysis to estimate or predict the DBH values if you had ALS data, but you would not be able to do the same level of detail that you can do in the TLS module to get those exact tree ring and DBH values.
Thanks. Next question is from Mark. Does photogrammetry-based point cloud work with LiDAR 360? I think we kind of addressed that earlier, and that was a yes, right,
Yeah.
Camille? Okay, perfect.
Yeah, that's right.
Okay, and let's see here, just going through some more questions here. So we'll go till about 12:10, and then if there's any unanswered questions, we'll be able to address them in an email format that we will send out after the rest of the questions here. So I think it's Amy is asking, she's asking if they're interested in the forestry module. Is a trial available for that as well?
Yes.
Oh, sorry. Yeah, I was going to say yes. So
yes.
The trial that we will be giving will give you access to the forestry, the terrain, and the power line as well. And then to also circle back to the question about the language, the software does allow a display method of English, French, Spanish, and then a few different other languages. You just change it within the display options.
Thanks, Cody. And then Scott asks, will we be able to determine when that key would begin a trial period? So I'm assuming it's more like a question of how long is the trial period for?
So these will be good for 15 days from the day that you actually activate the key.
Okay, and then Riley asks, does the software come in different packages, i.e. for forestry purposes with certain layers included?
So the key aspect is that there's the framework, the LiDAR 360 framework, and then as Dan was explaining, there's individual modules, and then so you would purchase the framework, and then you can purchase specific modules, which would be the terrain module, the forestry module, the power line module, and then the additional geology and mine module. Those you can purchase individually. So if you're just specifically looking to do tree segmentation or canopy height models, then you'll just look towards the forestry module.
Perfect. So Mike asks, how do you add ground points to the LiDAR data and recognize them? With photogrammetry, you visualize the type points together, and how does it work with LiDAR?
So the ground, I think what they're asking is how does the ground classification algorithm classify ground points? I think that's what that means.
It's more like how do you add ground control points to LiDAR data and be able to see it within the model? Yeah.
Oh, I see, how to add the ground control points. So like I had gone over, you'll be able to kind of reference this back to the section where I talk about using that control point report tool. Once you open that up, you can import your GCP, your ground control points into there in an XYZ text file format. And when you have that control point report window open, you'll be able to visualize if your GCPs are in the right coordinate system, if they match the same coordinate system as your point cloud, you will be able to see your GCPs kind of overlaid roughly where they should be. They'll pop up as these sort of red points that are numbered. If you don't see them when you load in that file, chances are you have the wrong coordinate system. So you might have to convert your GCPs or convert your reproject your LiDAR point cloud in that case.
I think kind of rephrasing the question, you might be asking like, so if you set out targets maybe in your LiDAR data collection area, like how would you be able to kind of visualize that, match it up
I see.
the target?
Okay. Yeah, so I mean, it really depends on the target. If you are using a LiDAR specific target where you have really good contrast in intensity values, so something that's like has good shininess essentially, contrast would be the best for LiDAR so that you could kind of pick that differentiation of the target, checkered target up in the intensity values of the LiDAR point cloud. So one of the visualization options on the left-hand side, you've got your display by height, display by RGB, and then there's a display by eye intensity. So you can use that intensity view to try to find the center of your GCP. Or if you have a colorized point cloud, if you say you had a LiDAR V70 with the camera module attached to it and you had colorized your point cloud, and you can see that black and white checkered target in your colorization, you can kind of easily pick out the center from that and then kind of reference it to the intensity values to do that sort of horizontal accuracy. But yeah, it's definitely a little bit harder to pick out a target if you don't have colorization data, or if you can't see it in the intensity view because there's not enough contrast in the LiDAR is in a near infrared part of the spectrum, so it's not what our eyes can see, so it needs to have high contrast in the near infrared.
Thank you, Camille. So a question from Josh. So he's asking, does CanDrone offer LiDAR training for someone completely new to the technology? What is the cost, and if not, who do you recommend? So I can answer this question. Yes, we do offer training for LiDAR specific applications, and you can reach out to us if you are interested in this, and we can get you some pricing and what that entails here. So we're heading at 12:06 here. We got a ton of questions, so we're gonna try my best to pick up the main questions, and then like I said, we'll address them in an email after that. So let's see here. Coming late. So Jared asked, can you speak briefly on the coordinate system LiDAR is captured in, and whether LiDAR 360 can get it in local coordinates?
Yeah, so if you have a GBI system like the LiDAR V70 or V, when you're in LiDAR reference, the kind of the base coordinate system that it's using is WGS84 and ellipsoidal heights. So that's sort of the root origin from it. And then in LiDAR reference or in LiDAR 360, there are options to reproject that data into a different datum or projection. Often lots of people have the kind of specific questions about, transferring the ellipsoidal heights of the Z values into orthometric heights, or kind of the local coordinate systems in the US in feet, and that can kind of get a little bit tricky with some of the specifics. So if you have kind of further questions on that, we would recommend doing some LiDAR 360 training with us, because it's a little bit more involved sometimes, and you want to make sure you're getting that stuff right. But essentially, yes, that it's possible to change those into a local coordinate system.
Awesome, thanks, Camille. So we'll wrap up the Q&A session here. I know there's a lot more questions, and I apologize if we couldn't get to them. And like I said, we'll address them in an email to follow up. So just to wrap up everything, again, I'd like to thank everybody for their time to join our webinar today. And just as a reminder, Candrone is a full-service technology company that provides sales, rentals, training, and services. And we're a GVI authorized dealer. So we'd be happy to help you out with any GVI software solution or hardware solution. And to be sure to follow us on our social media for upcoming webinars. You can visit our website to look at our full lineup of products and services. You can always also contact us at support@candrone.com, and you have our personal email, so you can feel free to reach us out to us at any time.